Things in space look a whole lot cooler than here on Earth. Welcome back, guys. Today's video is on the top 5 amazing space experiments.
How do you wash your hands with soap and water in space?
Number 5. Canadian astronaut Chris Hadfield experiments with a new pack of hand washing solution and demonstrates how to properly wash your hands in space.
It is no rinse body bath. No rinse body bath. And it's a bag with a straw. So now let's demonstrate. Okay, it's time to get clean. I'm going to squirt some water out. So we have a big ball of water, and you put it on your hand. And now I've got water floating around on my hand. And so I wash my hands up with that. And then grab a towel. And dry them off. So that's how we do it. We use no rinse. It's a special type of slightly soapy water, so you don't need to have a bunch of fresh water afterwards. You squirt it, you float a ball of water in front of yourself, and then you just dry your towel. And when you're done, we just tuck our towel somewhere to let it air dry so that the evaporated water gets back into the space station and we can use that water again. So it works pretty well. Sort of like, maybe sort of like if you were on a sailboat and you needed to get clean, you do it sort of the same way.
Number 4. An astronaut experiments with water physics in a weightless environment. It's really trippy to see how the water reacts.
Wow. Cool. Wow, I just love those oscillations. There we go. Okay. Let me switch it to a black background. Yeah, so that's about 800 mils. So this should put it around 1100 milliliters. Let's see what happens here. Oh, I just love that. Look at that. Amazing. Just one of these jaw-dropping moments. Okay, here we go to do it again, looking into the camera. Big puff. Here we go. Oh, right at the lens. I saved the lens. What I'm planning to do is, after this whole series of experiments, I'll suck all this water up with a syringe, I'll put it back in bags, and I'll use it to make tea with, so I'll end up drinking my experiment. You gotta conserve your resources when you're in the frontier. You don't get to see this as common, intuitive observables on Earth. And so when we go into a frontier, our normal Earth-honed intuition no longer applies. And this rule works in space, and I can't. And instead of putting a puff of air on it, I'm going to put a puff of water. This is going to have a lot more momentum in it than the air. Whoa, whoa, I was afraid. Oh, look at that, cool. I squirted water through. Oh, isn't that cool? The water in the sphere went around the air cavity and formed a huge bubble. Wow. Oh, that is so cool.
Number 3. European astronaut Tim Peake tests how the body responds to being dizzy in space.
And does it make me feel unwell? So I'm going to get Tim to spin me around doing something that would probably make me feel quite sick down on Earth. So let's see how that goes. This could be the worst idea I've ever had.
Come on, you can do better than that.
Okay, so yeah, I'll just go into a ball and start spinning. And then if you want to just keep me go round. And
On axis?
yeah, on axis, that's cool. Actually, it's more provocative when you go off axis.
Yeah, I'm not sure if you even control it.
Yeah, no, don't worry. Provocative's fine. Just keep it going.
Going faster?
Yeah. Let's go for it. That's good. And Okay, I'll see if I can. I'm feeling dizzy. I'll see how quickly it stops. So it definitely felt dizzy initially, and now it's gone.
No, is that quick?
Yeah, completely normal.
Amazing.
Yeah, and again, I wouldn't be able to kind of just get off a fairground ride spinning that quickly for so long. I feel normal. Yeah.
Crazy.
It is amazing.
Number 2. Students from Nova Scotia asked Chris Hadfield to wring out water from a cloth. The results are unexpectedly quite interesting.
We may have the coolest washcloths ever here on the space station. I'm going to show you. Here's one of our washcloths. And it's compacted. It's put down into this little tiny hockey puck so that it saves space. But when you open up a hockey puck, and so when you open up your hockey puck and turn it into a washcloth, it was compressed in a great big vise somewhere. Okay, so here's my washcloth, like a magic trick. And now I'm going to get this soaking wet, and then we're going to see what'll happen when we wring it out. Meredith and Kendra suggested that I dip this in a bag, but bags don't hold water in space, so instead I filled a water bag. This has drinking water in it. And I'm going to squirt a bunch of water into this washcloth. Okay, so here's a soaking wet washcloth. Get the microphone so you can hear me while I'm talking. And now let's start wringing it out. It's really wet. It's becoming a tube of water. The water's all over my hands. In fact, it wrings out of the cloth into my hands. And if I let go of the cloth carefully, the water sort of has it stick to my hand. Okay, so the experiment worked beautifully. And the answer to the question is, the water squeezes out of the cloth, and then because of the surface tension of the water, it actually runs along the surface of the cloth and then up into my hand, almost like you had Jello on your hands or gel on your hand, and it'll just stay there. Wonderful moisturizer on my hands. And the cloth doesn't really unravel itself. It just stays there floating like a dog's chew toy, soaking wet. Great experiment, worked perfectly. Meredith and Kendra, congratulations. Great idea.
So this has to be number 1. US astronaut Scott Kelly tests how various dyes interact with a floating ball of water. It's almost like he's creating a miniature planet.
Scott Kelly aboard the International Space Station. I wanted to do a little demonstration of these paddles. They're called hydrophobic paddles, and they repel water, kind of like a raincoat. But up here on the space station, they allow you to play ping pong with a ball of water, and it's pretty cool.
Hello everybody, my name is Roy, and I'll be going to review some myths and misconceptions in astronomy with a little sprinkle of trivia. Okay, so let's begin with just a quick self-introduction. I just started to learn about astronomy when I was given an astronomy book on my 6th birthday by my mother. And ever since then, I was very interested in astronomy. And I am mostly interested in the theoretical side, including planetary, stellar, nuclear physics. So right now, I'm trying to learn more about stargazing and astrophoton. Practical side, I'm not that good, so learn more about it. Okay, so let's start off with myths and misconceptions. So we'll mainly be covering topics in the solar system, the major celestial objects in the solar system, and then at the end, we'll look through at some things that are not the solar system. So let's of course begin with the sun, which is not a planet. So what is the color of the sun? And over here, you can see a very misleading image, right, that I've placed here to bait your answers. So the color of the sun, many people will think is orange or yellow, especially many depictions of the sun will show it as orange and yellow. And when you look at sunlight, it is quite obviously yellow. However, the truth is that if you take a true color image of the sun, it will be white, pure white. In fact, that is a definition of white, which is all the different colors combined together. So why do we see it as yellow on Earth then? Because definitely our experiences are not wrong, right? So this is because the pure white light that comes from the sun enters the atmosphere. The blue light is scattered away. That is what makes the sky blue. So whatever light is left, you can think of it as white minus blue. And you can see here on this chart, white minus blue actually equals yellow. So this is why the sun appears yellow. If you were to leave the atmosphere of the Earth, for example, if you are on the International Space Station, maybe you are some rocket ship flying somewhere, you will actually see that the sun is white. Of course, don't look at the sun, but it will be white. Okay, the next myth is also that the sun is an ordinary star. I think some of you who have been reading quite deeply into astronomy, you will often hear this sentence to describe the sun. The sun is an ordinary star. Especially if you were to watch some of those comparison videos on YouTube, you see that the sun compared to several other stars that are huge like Betelgeuse, Antares, Rigel, Aldebaran, the sun is like a speck of dust. But the truth is that the sun is among the top 30% of masses of stars in the observable universe. So the truth is there are many, many, many stars that are smaller than the sun. And small stars are actually the majority of stars in the observable universe. Big stars, like the ones you saw earlier, are exceptions. It's kind of like how Singapore, you might think that you're not a rich man, but compared to all the people in this world, you're actually kind of rich. Yeah, this is kind of the same concept. So remember, if someone tells you that the sun is an ordinary star, not really. The sun is actually pretty special. Okay, let's look at the first two planets, Mercury and Venus. So as you can see here from this totally not to scale diagram of the solar system, you see that Mercury and Venus are the closest planets to the sun. So the question is, which is the hottest planet? Some of you might think that, since Mercury is closer to the sun, Mercury is definitely hotter. In fact, Mercury is almost twice as close to the sun as Venus is. But the truth couldn't be further than that Mercury is actually 430 degrees Celsius on the day side, and Venus on average is 470 degrees Celsius. So why? Why is this the case? As you can see from this picture over here, Mercury appears to be completely atmosphereless, if you can put it that way. There are no clouds at all. But if you look at this image of Venus here, it's covered by thick clouds for the entire surface. So these are actually clouds of sulfuric acid, and its atmosphere has over 90% carbon dioxide. Now, on Earth, we only have 0.04% carbon dioxide compared to over 90% on Venus. So this means that if Venus' atmosphere is the same as Earth, Venus will trap thousands of times more heat than Earth already. And what makes this even worse is that Venus's atmosphere is more than 100 times as thick as Earth. So you not only get the 90% carbon dioxide, you get an atmosphere that's actually thicker than Earth. So you get tens of thousands of times the greenhouse effects of that on Earth. In fact, day or night, it doesn't really matter to Venus. The temperature difference is barely 1 or 2 degrees Celsius. The entire planet is just choked with these clouds of carbon dioxide and sulfuric acid. So another cool fact about Mercury and Venus that people might not know is that Mercury and Venus do not have moons, or what in astronomy called natural satellites. As you can see in this image over here, every other planet in the solar system has moons. Even Mars here, with its tiny moons, Phobos and Deimos, which actually Deimos is actually smaller than Singapore. You can see over here. So there are even moons, like over here you can see Ganymede here, a moon of Jupiter, and Titan, a moon of Saturn, is actually bigger than Mercury. So next we're going to move on to Earth. So we're going to look at one cool fact, which is where does astronaut Cook go? And the next is we're going to look at the Great Wall of China. Can you really see the Great Wall of China from space? Okay, so to answer the first question, astronaut Cook actually gets burned in the atmosphere. So anything that is not of scientific value, any trash from the International Space Station that cannot be recycled and has no scientific value for scientists back on Earth, they are simply placed on a return craft and is burned in the atmosphere. So next time when you wish upon a shooting star, maybe just a small little percentage of that might just be astronaut poop. Okay, and then next we're going to look at is, can you see the Great Wall of China from space? So now this is a picture taken from the International Space Station, a zoom lens, by the way. And the International Space Station doesn't orbit the Earth very high up, maybe about 200 kilometers, 300 kilometers up. Where in this image do you think the Great Wall of China is? So some people might think the Great Wall of China is here, or the Great Wall of China is here. But the truth couldn't be further from that. This is actually a river and a road that is being built beside the river. This is also a road. The Great Wall of China is actually here on the bottom right to mid right of the image. So the Great Wall of China is too thin to be visible from space. There are many other things that are visible from space though. For example, our cities. So our cities, especially in the developed world, produce an insane amount of light, and most of the light that is not directed downwards, it goes straight up into space. So this is an actual image of Italy taken from the International Space Station, and you can see how bright the lights truly are. Okay, next we're going to move on to the moon. So I will address two myths here. One is that there's no gravity in space, and that the dark side of the moon is always dark. So here's a misconception: there's no gravity in space. There is. If not, the moon will not be in orbit around Earth. However, when we look at videos of people in the International Space Station, things always seem to float about, like as if there's no gravitational force to pull them down. So the truth is that this is because all of them are in free fall. It's akin to the sensation where you miss a step while you are going down a staircase and you sort of briefly for a moment fall a bit. When you fall, when you're in free fall, it will seem like there's no forces acting on you. But on Earth, there are always things around you that aren't falling. So you can always tell that, well, you're falling. However, in space, because everything is falling together at the same rate, at the same speed, it will appear as if nothing is moving because everything is moving at the same rate. So the truth is that gravity is about 90% that on Earth at the International Space Station. And this is what astronauts and scientists call micro-G, which is microgravity. But this does not mean that gravity is minuscule, micro, but rather that the effects of gravity are very small, microgravity. Okay, and the second misconception is that the dark side of the moon is always dark. So as you can see in this image of the two sides of the moon here, one on the left, the near side, is the more familiar one, right? Because we always see this side of the moon. Whereas the one on the right seems a little bit more alien because like that is definitely not what you picture in your mind when I ask you to picture the moon. So this is because the near side and the far side, which some people call the dark side, this only happens because there's what we call geosynchronous rotation. One side of the moon always faces us. This is because the moon, the time it takes for the moon to rotate about its axis once is very, very, very similar or almost the same as the time it takes to rotate around the Earth once. But this does not mean that the far side of the moon is dark. This doesn't mean we cannot see it. It means it does not receive any light from the sun. So let me try if I can make this thing work. Okay, here you can see the line here from the moon is pointing towards the Earth. So this is the near side. So we always see this side of the moon facing towards Earth. However, the far side, as you can see here, still receives sunlight as it slowly rotates towards the sun. So here is a new moon. We cannot see this side of the moon. And as the moon rotates around the Earth slowly, you can see that this is the full moon. When we see the full moon, when the near side is completely illuminated. So it is a myth that the far side of the moon is always dark. They spend equal amounts of time in the sun, about 14 days. Okay, next we move on to Mars. So Mars is a planet that always captures the imagination, especially when one is starting to learn astronomy. So I will not go through many myths or misconceptions. Instead, I'll give you a cool fact about Mars, is that there is this canyon system called the Valles Marineris that is actually caused by a tectonic activity that's related to the Darcy's bulge. Now, this is so many jargon and so many technical names. But what you can see here in this image, that huge scar that goes across Mars, that is the canyon that we're going to talk about. So this is the Valles Marineris up close. You can see that it is absolutely huge. Of course, you have nothing to scale, so I've put the Valles Marineris in the continental United States, and you can see that it's absolutely huge. It's more than 4,000 kilometers across, and it's extremely deep. It's way, way, way deeper than the Grand Canyon. So this is not formed by water. What is this caused by? This is caused by a formation, a geographical formation called Darcy's bulge, where my mouse is sitting here on the left side of the image. There are huge volcanoes here. Volcanoes so huge that they are 24 kilometers tall, which is really, really quite insane. They actually formed from a hotspot, for those of you who know geography. So the lava continuously comes out at one spot only. It does not change. It doesn't move from location to location, because Mars's tectonic activity is quite calm compared to Earth. So you have this system of volcanoes and a huge plateau. It's like there's a huge amount of rock there. It's so much rock that it cracks the ground beside it. And this crack is the Valles Marineris. So for those of you who learn geography, it's a graben formation caused by the plateau, the tectonic forces of the plateau, called the Darcy's bulge. Okay, let's move on to the next two celestial objects, Jupiter and Saturn. Now, Jupiter and Saturn are the largest planets in the solar system, and in total, they have more than 130 moons. So we're going to talk about the biggest one of them all, Jupiter. So Jupiter has 4 moons. Does it? This is what you always hear in astronomy. You will always see these 4 moons in the astronomy magazines, and you don't hear about any of other Jupiter's moons. So I have all of my friends that tell me that, no, Jupiter only has 4 moons. These are the 4 moons, the Galilean moons. Well, that is not true, but the Galilean moons are very, very interesting. And to me, they are the most interesting moons in the solar system. So they are thought to have formed together with Jupiter, just like as how the planets form with the sun. So you can think of Jupiter as a mini solar system with all the moons that are orbiting it. So, but Jupiter doesn't actually only have 4 moons. Jupiter has, as of now, 79 moons that we have discovered. But other than the 4 Galilean moons, all of the other moons are very, very tiny, and they seem to be captured asteroids. Because as you guys will have known, Jupiter is very big. Its gravity is massive. So a lot of the asteroids that fall towards Jupiter actually can become captured by its orbit. And here's a very interesting fact that you guys might not know, but the names of Jupiter's moons are not random. So if the moons, other than the Galilean moons, so other than Europa, Io, Ganymede, and Callisto, other than those moons ending in O and A are prograde. Prograde means they orbit in the same direction in which Jupiter spins. Retrograde, so retrograde moons end with E. These moons orbit in the reverse direction. So if Jupiter orbits clockwise, they orbit Jupiter anti-clockwise. So even their names make sense. Yeah, even their names have meaning, sorry. So what we're going to look at, of course, next is my favorite planet, Saturn. And the most striking thing about Saturn are its rings. Now, actually, all the 4 gas giants have rings: Jupiter, Saturn, Uranus, Neptune. But only Saturn's rings are the most striking to us because they are huge. So one thing that you guys might not know is that Saturn's rings are not actually solid. Because if you think about it, some of you might recall from your physics class, the closer you orbit to the planet, the faster you orbit. The further away you orbit, the slower you orbit. So if Saturn's rings were actually solid, they will start to break up over time since the inside orbits faster, outside orbits slower. So the truth about Saturn's rings is that they are actually made up of rocks and ice. So this is not a real, this is a computer generated image. And this is the closest image of Saturn's ring that we have actually captured using the Cassini orbiter. So Saturn's rings are made of countless tiny little particles from pebbles to the size of small houses. And this is what most people think asteroid belts look like. So the actual asteroid belt is nowhere near as dense as this. One asteroid to the next asteroid might be further than the distance between the Earth and the Moon. But in the rings of Saturn, they can be as close as like your next door neighbor. It is really, really that close. Okay, so next, we are going to look at Uranus and Neptune, the ice giants. So something that you might not know about Uranus is that Uranus is actually tilted, not as in it's angry or what, but is that it's the way it rotates about its axis and the way it rotates and the way it orbits around the sun is completely weird. So Earth has an axial tilt, that's how we get the seasons. But Earth's tilt is only about 23 degrees. Uranus, on the other hand, is over 90 degrees. So this means, right, that there are times where its north and south pole points directly at the sun. And if you can put yourself, if you can imagine this, you can take this as a thought experiment. If you place yourself at the equator of Uranus, on half of the year, the sun will rise from the east and set in the west. And on the other half of the year, the sun will rise in the west and set in the east. And in between these two phases, the sun will appear not to move in the sky. So I think that is really, really quite trippy if you are staying on Uranus. So as you can see over here, Uranus has rings as well, but these rings are extremely faint. They're mostly made of rocks and dust, very dark, very low albedo dust. Okay, so we go on to Neptune, the furthest planet away from the sun. In fact, Neptune is so far away from the sun and that there are no other like major planets, major objects in the vicinity, that Neptune as well, sort of like Jupiter, has a crazy collection of moons. So in fact, if you can see here, there are 2 moons, Semete and Niso. They actually orbit Neptune further away than Mercury orbits the sun. And they take more than 40 years just to orbit Neptune once. So this is only possible because there's a lot of space around Neptune. There are no other planets that can sort of steal its moons or move its moons around. So Neptune is this planet that's very far away at the edges of the solar system where nothing else is there. Yeah, and more cool stuff about Neptune that you guys might not know, because from what I've been seeing is that the ice giants are sort of neglected. Uranus can actually be colder than Neptune at times, even though Uranus is closer than Neptune to the sun. So some of you also might not know, Neptune is actually heavier than Uranus. So by putting all of this together, we can sort of gain an insight into why, despite the fact that Neptune is further away from the sun than Uranus, Uranus can still be colder. So I don't know if you guys have ever pumped a tire before, but you know, as the more you pump the tire, as the pressure gets higher and higher, your tire starts to get really hot. So the same thing seems to be happening with Neptune. Neptune is more massive than Uranus, but Neptune is smaller. So this could probably mean that Neptune has collapsed to a greater degree than Uranus, and all this gravitational potential energy is re-radiated out in the form of heat, and it heats Neptune to a higher temperature than Uranus. And to be very, very, very honest, no one theory now is currently accepted. Some people also think that this is because there's a higher amount of methane in Neptune's atmosphere. And this methane can act as a greenhouse gas. Even though Neptune is so far away, it can still heat up Neptune more than Uranus. Yeah, so this is something that is quite interesting. Okay, and for those people Now this is the one slide that is for those people who think that everything at the front is pretty. We already get it. How about something more interesting? So, I apologize to those who might not know a lot about some astronomy. To go very deep into astronomy. So I would want to try to bring you along with me. So nucleosynthesis is the formation of heavier elements from lighter elements. So most people would know, like when you study about supernova, studying about big stars and black holes, that the stellar fusion process ends in iron. However, this is not true. It actually ends in nickel 56. However, the reason why most people say it ends in iron is because this nickel decays back into iron. So, but the truth is, it ends at nickel 56. It's kind of like, the teachers are trying to skip one step and get to the final answer. However, this final answer misses out something very important, is that the radioactive decay from nickel 56 to iron 52 produces a lot of light. In fact, about 70% of the light of a supernova comes from the radioactive decay of nickel. So this is something that people who even studied very deep into astronomy might not have known or might have misconception about. Okay, so we are going to end off with the most common misconceptions that I've seen about astronomy. Is that sometimes people think that light years is a distance or is a measurement of time. Time because light years. But the truth is that 1 light year is the distance that light travels in a year. So it's actually a measurement of distance. So which is that crazy figure that you see over there. Next is that astrology is not astronomy. Astrology is a form of divination, i.e. you try to predict the future. Astronomy is a science. You look at it and you try to predict about those objects, not about things that are completely unrelated to those objects. So if next time you ever see someone who is particularly interested in astronomy, you say, oh, can you teach me about astrology? Now you know why they will look at you with funny eyes. Okay, so the next one is that actually to get into orbit around a planet, or in fact any object at all, you actually have to be moving sideways relative to that object's surface fast enough. The reason why rockets go up first is because it's easier to go sideways in space, because space has, well, almost negligible air friction, air resistance. So it's easy to go sideways fast in space, not while you are, banging into mountains, banging into high-rise buildings. Okay, and the last one is that some people think that the sun will explode in 5 billion years. Like, or when the sun is old already, the sun's going to explode and kill all of us. Well, it's going to kill all of us, but unfortunately not in such a gruesome manner. The sun will just get bigger and bigger and bigger and then swallow us. Okay, that's the simplification, but that's what's going to happen. The sun is not massive enough to explode in a supernova. Okay, with that, I know some of you guys might have some questions for me. If you have any questions about the presentation slides, I will be sharing my screen again. So if your questions can also be not about these slides. If you have any other questions, things that you want to clear up about astronomy, you can ask me as well.
So you guys can either type in the chat or unmute yourself. Actually, let me ask a question first.
Sure.
If we go back,
yeah, sure.
So if we go back to the slide that shows the 2 faces, you can consider like 2 sides of the moon, right? Why is it so different?
Well, that's a really difficult question. For the benefit of those people who might not be able to follow, please type inside the chat if you do not understand any of the terms that I'll be using later. Like I mean, they'll be using soon. So as you can see, right, the near side of the moon has many of these black patches. So these black patches, we know them in English as seas, as in like the place that you go to put your boat, seas. And the proper term will be mares, or Latin for seas. So on the right side, you see that there's only one sea here. Whereas on the left, you have a few of them. In fact, one of them is called an ocean because it's so big. So the question will be, why does the near side of the moon, i.e. the side that we always see, has so many more seas than the far side? So the question that we need to ask ourselves next is, what are the seas? So the seas are large flat plains compared to the rest of the moon. So the rest of the moon, you have dozens of craters, especially, can you see my mouse over here? Or you can't see my mouse, is it? Okay, you can see. Okay, so if you look on the near side here, you see a crater over here that shoots out all the different things. Yeah, so most of the moon is covered with these countless of little craters. But on the seas, there are far fewer craters. There still are craters, but far fewer. So this sort of indicates to us that the seas are sort of repaved. Like, you know, the roads, if you have too many potholes, then you repave the road. So this is something like that. So this means that the seas must have formed much later than compared to some of these craters. So they are actually formed by asteroid impacts. The asteroid hit the moon and it broke through the crust of the moon so deep that the magma from the mantle of the moon rise up and sort of repave the ground with a very nice layer of basalt. Basalt is a very dark colored igneous rock. So then that sort of pushes the question back one more step. Why does the near side of the moon get hit with asteroids, whereas the far side of the moon doesn't get hit with asteroids? Right, because the near side has so many more seas. So this is actually a bit misleading, because if you can think of it this way, the far side of the moon always doesn't face the Earth. If you think about it in the sense that the asteroids can come from anywhere and is attracted by Earth and moon's gravity towards Earth, then you would expect the far side to be hit far more often than the near side of the moon, because it's sort of like the back side of the moon is like facing out, it's acting as a shield for Earth. So it cannot be that reason as well. It cannot be that the far side gets hit with less asteroids than the near side. If anything, the near side should be hit less. So the sort of real reason and the final level that we are going to be going to for this session anyway, is that the near side of the moon, the crust of the near side of the moon is far thinner than the far side. In fact, it's about 10 to 16 kilometers thinner. So this means that when the asteroids do hit the moon, it is easier to sort of punch through the thin crust on the near side than it is for the far side. So the far side crust is very thick. So most asteroids aren't strong enough to punch straight through the crust. So this is the reason why the near side of the moon is so colorful in a sense, whereas the far side is pretty bland. Yeah. So is any other questions from you guys? Maybe one that is not so difficult. It can be anything about Astro as well, if you have a question about Astro.
About the question whether the slides or recording will be available to us. So if you would like to, we can post it into the Telegram group where you can access it after today. Okay, let me ask another question.
Sure.
So if you go to the slide with the stars, right?
Stars, okay. This one?
Yeah.
Whoa, sorry. This one?
Yeah.
Oh, this one?
The previous one.
Oh, the previous one, okay.
So why is it always that the only colors that you see that is always like represented like orange or yellow or like blue?
Okay, so this requires some physics and biological knowledge. So the first thing that you guys need to know is the black body spectrum. So the black body spectrum is the radiation that is put out by a body as it gets hotter. So for example, maybe it's kind of intuitive to you guys. If a metal gets hotter and hotter and hotter, it starts to glow red, right? Then it gets hotter and hotter, it starts to glow orange, and then yellow, and then white. So we call it like white hot, right? So that is a black body spectrum. If you were to look at it, it will look something like a curve that's very steep at the front, then sort of peters off at the end. So where this peak hits is called black body peak spectrum. So this spectrum moves more and more to energetic levels the hotter the object gets. So for example, a human body doesn't glow, right? We don't really glow in the visible light, even though we are hot, because we are not hot enough. For these stars, they will glow red if they're cool. So anywhere from 3,500 Kelvin to about 4,000 Kelvin, you will glow sort of a dull red. So over here, you can see Betelgeuse. Betelgeuse is a red supergiant. So it's pretty cool. In fact, it is cool enough that in its atmosphere, you can actually have solids because there's certain metal compounds that don't melt at the temperature. Yeah, just pretty cool. You can get tungsten and related metals that condense in this atmosphere of Betelgeuse. So as you get hotter and hotter, you start to become yellow. Not like the sun. Remember, the sun is white. So you have orange supergiants like Antares. And as you get hotter and hotter, you get white stars. For example, the sun. I know the sun is also called a yellow dwarf, but that's how astronomy names things. I can't control that. And the hotter you get stars like Sirius. Yeah, the star is called Sirius, as in like Sirius Black, if those of you who watch Harry Potter. So Sirius is whitish blue. It's like sort of like, the fluorescent lights that you get. It's a kind of very harsh white color, not like the pleasant, warm white color from the sun. And if you get really, really, really hot, you get this whitish blue color like you see here in Rigel. Rigel is a blue giant. So the spectrum that you get from a black body goes from dark red to orange to white to light blue, and finally only the hottest stars are ever blue. Not deep blue, but blue. So the question is, why aren't there more colors? For example, if you look at the rainbow goes from, well, I'm not a primary school teacher, but Roy G. Biff, right? Red, orange, yellow, green, indigo, violet. So you're missing green, that's one, and you're missing violet or purple. You can just call it purple. So the thing about green is that you need to know about biology, how we sense green. So we have 3 cones in the eye, red, green, blue, and there must be a certain activation level of each cone to tell you that, oh, it's green. So unfortunately, even if the peak emission spectrum of an object is in green, you will never see it as green because it's also emitting the lights of other colors. And when the lights of other colors hit your eyes together with this green, you no longer perceive it as green. You perceive it as something like white. So in fact, our sun's peak emission spectrum is somewhere near green, but the sun appears to us as white because the sun also produces red, the sun also produces blue. And when all of this combines together, you get white. You can never isolate green. Same with violet, same with purple. So purple is all the way on the other end of the spectrum, the super energetic spectrum. A star that can produce purple light, which is like super hot, will also be producing a lot of red light, orange light, yellow light. And when you combine all of this, you still get a blue color. So you can Google this star cluster called the Pleiades. It's a very, very beautiful blue. And I think that is one of my most favorite blue colors. There are also stars like Wolf-Rayet stars, which are almost tending towards purple. They're really on the limit because their surfaces can be as hot as 50,000 Kelvin, which is 10 times hotter than the sun. And that's just the surface. So at that temperatures, they can reach near purple, but they will never appear purple to our eyes. Yeah, so this is more of a biological thing than a physical thing. Yeah. And that also explains why there are no green stars, in case you guys are wondering. Yep. Okay, so there's a question here. In the early age of the universe, the effect of time dilation should be more pronounced due to the strong gravity. So when they say shortly after the beginning of the universe, protons and neutrons form within the first few minutes, what time scales are these times reported in? And does this affect how we measure the age of the universe? Now, this is a even harder question. Okay, so we measure everything through a relative scale. For example, because right now in the current observable universe, there are areas of the universe which are flat as in no massive objects, no radiation, almost negligible amounts of radiation. And we have parts of the universe which are extremely dense or curved because they have a large concentration of mass. For example, near the centers of superclusters, like the Virgo supercluster. So by taking a comparison between these two, we can sort of understand that there are some parts of the universe which the time moves slower than the other parts. So in a sense, you can think of it as the bed is not equal. There are some parts of the bed which is like somebody sitting on the bed, so it's like curved. Some part of the bed is no one sitting there, so it's flat. But right at the start of the universe, because everything is equally dense, even though it's extremely dense, everything is still flat. So a way you can think of it is, if the universe at the start is so incredibly dense, why didn't the entire universe just collapse back into a black hole? The reason why the universe did not collapse into just one black hole and the whole universe doesn't exist is because everything is pulling on everything with the same amount of force, such that there is no force. You can think of it as, if you have $10,000, I have $10,000, and he has $10,000, then who is rich? No one is rich because we all have the same amount of money. So because every part of, not say every part, but most of the parts of the universe are at the equivalent density, such that they pull on each other, that there is no perceivable curvature. It is only after this period called inflation, which you will get a differentiation of matter and areas without matter called voids. So time would still appear to move, well, relative to us anyway. Normally, it does not slow because there's nothing to slow it down. There is no part of the universe where it's moving faster. There's no part of the universe where it's moving slow, because almost everywhere in the universe is at the same density. So something that will be more interesting maybe for you guys to find out, because if you can find out, you can win a Nobel Prize. Why is the universe at this state at the start? Why is it so beautifully smooth? It's only now it's like very crumpled, like some parts have more than things than the others. If you can figure out why the universe is so smooth at the start, you can definitely win a Nobel Prize. Because this is a long-standing problem in cosmology. It's called the low entropy problem, which is why the universe started from a state of low entropy and is slowly tending towards high entropy now. Yeah, if you can answer that, that'd be great. Yeah. So it does not affect, sorry, to answer the last question, it does not affect the way we measure the age of the universe. The way we measure the age of the universe now, the most reliable one anyway, is through the measurement of this thing called the cosmic microwave background. It is the light that is released after reionization. I know, a lot of technical terms, a lot of blah, blah, blah. So I can go a little bit into this. Bear with me, guys, if you don't have much of a physics background. But when the universe form is very hot, so when things are very hot, they exist in another state of matter called plasma. I think some of you have heard of it before. So a plasma is when the electrons of molecules, electrons of atoms, are no longer bound to the atom. So they sort of go anywhere they want. They're not bound to the atom. And when this happens, light cannot travel freely. So light can travel through gas, right? I mean, you can see things after all, but light cannot travel freely through a plasma. As light moves, it keeps banging into these electrons and it cannot get anywhere, and it gets absorbed, reabsorbed, and then re-emitted and whatnot. So light cannot travel. But as the universe slowly cool down, the plasma turns into a gas. And so there's this period about 300 to 400,000 years ago, I think it's 380,000 years ago, where most of the plasma in the universe slowly transited towards gas. And during this period, most of the light of the universe can finally travel free. So during this moment where the light is sort of released from the plasma, over the years since the start of the Big Bang, this light has been slowly been stretched. So from the cosmic background microwave radiation, the information that's imprinted in the light, we can sort of rewind the clock in a sense and see, not see, but do some observations to guess as to how old the universe is. So I think the current estimate is like 13.7 or 13.8. Yeah, if I'm not wrong. So it does not affect the fact that the start of the universe is so dense. Okay, maybe we can have one more question, one more hard question, or a few more, maybe like, why does Venus orbit, why does Venus rotate in the wrong direction or whatsoever? Anyone else has any burning questions?
I have one question about burning things.
Oh, okay, sure.
So, you know, like upon re-entry into a, then like the things burns, right? But how come when they are exiting, they don't like burn?
Oh, this is very good, very good. So, there's this thing called max Q. I'm not sure if, so some of you who have followed SpaceX launch, right? You know, when they're launching the rockets into space, and they go like, oh, this is where this thing happens. This is where that thing happens. So there's one part where they call max Q. So max Q is called maximum aerodynamic pressure. It is when the rocket is starting to get fast, and the air pressure, the force of the resistance of the air on the rocket is as high as it gets. Because if you think about it, the higher you go, the less air there is. So after a certain point, the air doesn't really matter. But when you're near to Earth, even though the air is very thick, you're not moving very fast, right? So there must be some point where it's like kind of like doing differentiation, where it's like, you know, but instead of the bottom is like the top. So when you're traveling fast and the atmosphere is still thick enough to matter, so this is called max Q. And max Q must be calculated such that the rocket doesn't burn and the rocket doesn't break up. So when they're launching rockets into space, it never exceeds Mach 5 through the lower atmosphere, somewhere between the troposphere and stratosphere. Because if it actually goes fast enough, then it will burn. It will burn in the atmosphere. So re-entry speeds, you're looking at about 22,000 kilometers per hour. That's like 18 times the speed of sound, assuming that the speed of sound is same as that on sea level. So at that temperatures, the truth is that it's not really air friction that is heating things up. This is a myth and misconception again. Most people think that it's because air friction causes the thing to heat up. But the truth is that it's not air friction. It is compression. You can think of it as you are moving your hand through the water. The water in front of your hand must move out of the way, because if the water doesn't move out of the way, then you cannot move your hand. So, but the faster and faster you move, the less and less time you give for the water in front of your hand to move out of the way. And when you exceed certain speeds, I think it's, don't quote me here, I think some MAE students can probably answer this better than me, but when you go past Mach 8, I think, there comes an area where you get shock waves that propagate from the spacecraft outwards. And this causes compressive heating. Kind of like why I say just now, you pump a bicycle, right? The more you compress the gas, the hotter it gets. So you compress the air in front of you to such temperatures that it starts to become a plasma. Yeah, so that is what actually causes the heat. So this is why people can still survive to come back to Earth. Because if it's really friction with the air, the friction will have killed everyone on the spacecraft already, because the heat is directly touching the spacecraft. But the truth is that it is actually a air pocket in front of the spaceship, which is super hot. So you can actually stand at the back of the spaceship and still bring back ice cubes. Yeah, it's just the front of the spaceship. So to answer again, just to summarize, if your rocket is moving fast enough through the atmosphere, it will burn. But of course, engineers are smart enough to have calculated this way beforehand so that they don't exceed the speed limit at that air density so that it doesn't burn up. Things that come in from space usually travel very fast speeds because they're falling to Earth and the gravity of Earth is pulling them. So they reach speeds anywhere from 10 times the speed of sound up to 60 times the speed of sound. So at that speed, you will compress the air in front so much that it heats up and produces a fireball. Yeah. Okay. Any more questions from the from our dearest members of public? Okay. So this is a pretty high level question as well. So for those of you who are not, maybe who have never seen this before, the thing that sustain stars, allow stars to no, it is okay. So there are many different classes of stars. So you have if from white dwarfs all the way up to O giants. So the less massive stars fuse lithium, beryllium, and deuterium. When you get higher up, you get the main sequence stars. So they usually go pp1. So I hope you know what I mean. Proton one chain. So proton one chain just takes 4 protons, changes it into helium-4. So as when the temperature gets higher, you get increasing percentage of other proton chains. So in the sun, pp1 is the highest percentage, but you have pp2, pp3. So the difference between these three is that you're not using one H protium to form helium. You are starting with deuterium. You are starting with tritium, different isotopes of hydrogen. So they're all proton chain. So Yu Yang mentioned something over here there, CNO. CNO is called the carbon nitrogen oxygen cycle. So that is actually a catalytic cycle. So it goes through the different isotopes of carbon, nitrogen, and oxygen. And this is dominant in stars that are about 1.5 to 2 times the mass of the sun. So this one is the one that he says over here, CNO. So in really high mass stars, you actually get this thing called the triple alpha process. So CNO still is very dominant in heavier stars, but you have this thing called the triple alpha process. So why triple alpha process only dominates at very massive stars is that their cores have enough pressure to fuse helium. So triple alpha, when you hear the word alpha think helium nucleus. Helium nucleus has 2 protons. So you think about it, 1 positive charge, hydrogen, 1 positive hydrogen, you try to force them together, there's positive, they try to repel each other, right? But if you have helium is 2 protons, it is way harder to fuse 2 helium than just 2 protons. So at very high mass stars, their cores are under very high pressure. The temperatures are very high. So the kinetic energy of those nuclei are high as well. So in those cases, the triple alpha process will be dominant in the core. In the layer above, still in the core, but in the layer above it, CNO is dominant because CNO is a very efficient way for stars to produce energy. Then in the layer slightly above, you get PP chain. So as the stars age and as the star's core collapses, your center becomes helium burning, which is what I've been talking about just now in this slide. Here. So I end off with the silicon burning. So silicon is the last step. You're still fusing helium nuclei until you end up with nickel. So sometimes you get cobalt as well. Sometimes you get some weird thing because of other particles that randomly just bang into your nuclei. But on average, you get nickel. So this is a extremely deep question. This is a very good question. Carbon, nitrogen, oxygen cycle, and the fact that not all stars use the same nuclear fusion process to produce energy. This is an excellent question.